Hello, pre-calcers. This is Mrs. Leopold, and I'm going to talk you guys through notes number 4. I don't think you really need the notes, so if you want to try on your own, you probably should just try to read through the example, see if you can figure it out on your own. But if not, I will take you through the answer key. My board hasn't been working very well, so I'm going to go ahead and walk you through this answer key provided by Miss Bright. So far we have talked about arithmetic different sequences and series and geometric sequences and series. And the new sequence we're going to talk about today is the quadratic sequence. So in an arithmetic sequence, we had first common differences, and that led to some kind of explicit equation, which was always linear because it had a common difference, or in other words, that was like a slope. So if we look at this sequence right here, there's a common difference of -3. So we take that -3, multiply it by n, and then you can plug in the number 1. So -3 times 1 would be -3. So what number do we have to add to -3 to get to 4? We would add 7. Or you could just go backwards and figure out what the term would be in front of it. So in other words, our explicit rule would be a sub n equals 7 minus 3n. That's just for a simple, straightforward arithmetic sequence. For a quadratic sequence, it doesn't have a common first difference, but it has a common or constant second difference. So in this pattern, or in this sequence 4, 7, 12, 19, 28, which was provided here, we can calculate our first differences. So difference of 3, 5, 7, and 9. They are not common. However, when we do our second difference, we see that yes, indeed, they are constant. So here is your constant second difference that is in common. Since the second differences are constant, then we know we have a quadratic equation. So we define a quadratic equation. This is the term. So t sub n just is identifying the term. So t sub 1 would be the first term, t sub 2 would be the second term. And we're going to calculate the first term by plugging in a 1 for n. So if we plug in a 1 for n, we would get a times 1 squared, which would be a, plus b times 1, which would be b, plus c. So our first term is represented, or equals a plus b plus c. So we can set up a system of equations to figure out what the relationship is between each term. So in our second term, we plug in a 2 for n. So 2 squared is 4, so we get 4a plus 2 times b, which is 2b plus c. And we can continue that pattern, plug in a 3 for n, 3 squared is 9, so we get 9a plus 3 times b plus c, etc. So if you look at it all together, the quadratic sequence, this is your first term. Your second term can be written as 4a plus 2b plus c. Your third term can be rewritten as 9a plus 3b plus c. And then we would continue. The fourth term could be written as 16a plus 4b plus c. So there we have it. So now, sorry, I need to get to the next page. Okay, so now we have our now we're moving on. Our next thing we need to do is to calculate what our first and second differences are. So if we were to subtract 4a plus 2b plus c minus a minus b minus c, our first difference would be 3a plus b. If we were to subtract our third term from our second term, 9a minus 4a, we would get 5a. 3a minus 2b, we would get b, and c minus c, there wouldn't be anything. So our first difference between the first two terms is 3a plus b. Our first difference between the second two terms is 5a plus b. We could do it again between term 4 and 3. 16a minus 9a is 7a. 4b minus 3b is b. And then, of course, our c's cancel. So this is our third difference. Well, they are not the same, but when we take the second first difference, did that make sense? We take 5a plus b minus 3a plus b, so 5a minus 3a is 2a. b minus b is nothing, so we get 2a. And then we take the difference between these two terms, or these two differences, we would get 2a again. So we have a common or constant second difference. So what you'll notice, or let's just follow this process, yeah, for an example. So we have this sequence, and we did the common differences already, so we see the second common difference is 2. Well, what this means is if the second common difference is 2, we've just proven formulaically that the second common difference is equal to, algebraically, the expression 2a. So we can take the second common difference in this original sequence here and set it equal to the second difference above. So we just set 2a equal to 2, so therefore a is going to equal 1. Then you go back and we have this formula. This is going to be, these results are going to be the same every single time, no matter what the sequence is. So we go back and we have this first difference, which is 3a plus b. Well, we now solved for a. A is equal to 2, so we put in 2 for a. So 3a plus 2, or sorry, 3 times 1, sorry, a is equal to 1. 3 times 1 plus b equals 3. Now, why is that 3? Because that is what our first difference is between 4 and 7, and that's what 3a plus b represents, is the first difference between the first two terms. So we set that equal to 3 right here. We subtract 3 from both sides, so b equals 0. Then we know that our very first term is just equal to a plus b plus c. So a plus b plus c must equal 4, because that's what our first term is here. And we know that a equals 1. We know b equals 0. So of course 4 would then equal a, which is 1, plus b, which is 0, plus c. So therefore we can see that c is equal to 3. So when we plug that in, a, b, and c, we said a was equal to 1, b was equal to 0, and c was equal to 3. So remember that the original formula, or original where we got this from, was on the other page, which was your t, your t equals a sub n squared plus b n, or sorry, a times n squared plus bn plus c. So that is what we are now substituting our a, b, and c in here. So this is our general, or our explicit rule for this particular sequence. It's quadratic because it has n to the second power, and then once we substituted in a, b, and c, we just got n squared plus 3. You can go do a little check. So plug in a 1, 1 squared plus 3 is equal to 4. Yes, that was the first term. Plug in a 2, 2 squared plus 3 is equal to 4 plus 3, which is 7. So yep, you can see that we did get this sequence, which was our original sequence. Now what happens if we want to make a recursive rule instead of an explicit rule? We actually just need to look at the pattern again. Your recursive rule, remember, you always have to use the term before the one that you're trying to find. So if we're trying to find the third term, we need to use the second term in our recursive rule. If you want to find the seventh term, you have to have the sixth term in order to find the seventh term. So your recursive rule is actually quite simple. Look at your first difference here. Your first difference is linear. So we're going to use this linear relationship to find our recursive rule. If we have, remember, we also have to define the first term. So our first term is equal to 4. Let's make a rule or explicit rule for this first difference. So we have a common difference of 2 in between the 3 and the 5. That's how we got our 2n right here. If you plug in a 1, we're going to have 2. So what do we have to do to 2 to get to 3? We have to add 1 to it. So here is my explicit rule for this first difference. Well, if you take the first term of 4, if we want to get the second term, we just plug in a 1 here. So we would take the first term, which is 4, and we would add that linear relationship to get the next term. If we take the second term, we would add the linear relationship to get the third term. If we take the third term, we add the linear relationship to get the fourth term, etc., etc., and you can see how that works right here. All right, now I think it's just practice time for you. You probably don't really need to look at this. You just need to try on your own. Actually, this first one, you should definitely just plug in. You shouldn't need any help from me explaining that. You can pause and do it on your own and see if you got it right. But I will go ahead and talk you through, excuse me, example number 2. So here we have a relationship, for example, 2 of the sequence. It's 4, 6, 14, 28, and 48. When you do your first common difference, you get a difference of 2, 8, 14, and 20. Then do your second common difference, or your second difference, which is common. So your first difference is not common, sorry, and your second difference is common, which means it's a quadratic relationship. Well, we learned from our previous investigation that you can take your second common difference and set it equal to 2a, because all of the time your second common difference is going to equal 2a. So your second common difference, 2a equals 6, you divide by 2, you get a equal to 3. We learned that our first common difference of 2 is always going to equal 3a plus b. So we know a is equal to 3, so we plug that in. We get 3 times 3 plus b equals 2. So we subtract 9 from 2 to get b equals negative 7. And then we learned from our previous investigation that a plus b plus c gives us our first term. So we know our a, we know our b, we add it to c to get 4, and then we learn that c is equal to 8. So remember, a is the coefficient in front of your n squared, b is the coefficient in front of n, and c is your constant, which is 8 in this case. So to find any term of the sequence, t sub n, your explicit rule is 3n squared minus 7n plus 8. To find the recursive rule, you would make the second difference into a linear relationship, which is here, right? So common difference of 6. When you plug in a 1, you get a 6, but we have to make that number go down to 2, so we subtract 4. So our linear relationship is 6n minus 4. This over here should be a 6. Our first term is a 2, our common difference is 6. And then we just simply add that onto t sub n. And then don't forget, we have to identify what our first term is. So t sub 1 equals 4. And then t sub n plus 1 equals t sub n plus the linear relationship, which is 6n minus 4. Okay, I think you should practice again, and then you can check your answer key. So go ahead and pause, do example 3 on your own, and then you can come back and check it here when you're finished. So pause. All right, we had our relationship 3, 12, 27, 48, and 75 was our original sequence. First difference was 9, 15, 21, 27. The second difference is common or constant, so we have 6, 6, and 6. Remember, your second difference is always equal to 2a, so we find that a equals 3. Our first difference is always equal to 3a plus b, so we get 3 times 3 plus b equals 9, which b equals 0. And then our first term is always equal to a plus b plus c, which is equal to 3 in this case, and so we plug in the numbers and we get c equal to 3. Therefore, when we plug it into our relationship, we get 3n squared plus 0n, and then this should have a plus 3 right here. So 3n squared plus 0n, or just leave that out, and then plus 3 is your constant. What's our recursive rule? Well, we have a common difference of 6. We have this first term here of 9. So we have our 6n. If you plug in a 1, what do you do to get to 9? You have to add 3, so that's our linear relationship. We identify what our first term is. Therefore, t sub n plus 1, identifying into recursive relationship, t sub n plus 1 equals t sub n plus 3 plus 6n. And that's it. You can try the challenge on your own and check the answer key in the student files. Good luck. Please ask your teacher if you have any questions. It's kind of hard to explain on a video. So if you ever have any questions, please see any one of us pre-calc teachers. Thanks.